Welcome back, everyone. This will be our first lecture for Unit 1-2, Inferential Statistics. In this lecture, we will cover procedures for hypothesis testing, interspersed with discussions on point and interval estimation. And then we will discuss what hypothesis testing is and why learning it is beneficial. And then under hypothesis testing, we will discuss single means as well as comparisons between means under different cases. As usual, before we start with this lecture's topics, let's first have a review question. What is an estimator and what are the most important properties of a good estimator? So if you recall, an estimator is a statistic that corresponds to an unknown parameter. And two of the most important properties of a good estimator are: one, it is unbiased, meaning its long-run average should be equal to the parameter being estimated. And two, the estimator should have minimum variance. That is, it should have a smaller variance than any other possible estimator. Okay, so for our discussion today, we will assume that the experiments we will be dealing with are completely randomized experimental design. Okay, so this lends the data from a random sample from a normal distribution. Now recall our Portland cement example. In this experiment, the engineer wanted to determine the impact of adding a polymer latex emulsion during mixing to tension bond strength of the mortar. The original and the new formulations are the levels of the factor, which is tension bond strength. Now let y1, y12 to y1 sub n1 represent the n1 observations from the first factor level, and let y21, y22 to y2n sub 2 represent the n2 observations from the second factor level. We assume that both samples are drawn from independent and normally distributed populations, or NID. Then a statistical model that can describe our data would be shown on the slide, okay? Where y sub ij is the jth observation here for the ith factor level. Mu sub I is the mean for the ith factor level, and eta I sub j is the random error. It is a random variable associated with the ijth observation. Now we also assume that eta I sub j are normally and independently distributed with mean 0 and variance sigma squared. One of the first steps is usually to come up with a statement of the statistical hypothesis. Okay, and this usually stems from the problem that is being answered in the experiment. Now, for our example, our main question is that are the tension bond strengths of the two mortar formulations, that is the two factor levels, the same? Or stated another way, are the means of the bond strengths for the two mortar formulations equal? So with the statistical hypothesis, we come up with conjectures about the parameters of a model or that of a probability distribution. Now, in our case, our initial hypothesis is that the two are equal. Now, before we proceed further, let me introduce to you a recommended flow of the different steps that one would usually undertake when conducting a hypothesis test, okay, as shown in the figure to the right. So I already tried to streamline the figure, but the words in the figure correspond to the different steps, where the first step is to identify the parameter of interest And this, of course, will stem from the problem context. The second is to state the null hypothesis, and we usually call the null hypothesis H naught. And along with this, we specify an appropriate alternative hypothesis, usually called H1. And then we choose a significance level alpha, and along with this, a suitably small level of data. And then after stating or choosing the significance level, we then proceed to identify the test statistic that is appropriate for the hypothesis test. And then after that, we state the critical region, or the region for which the statistic will be rejected. And then second to the last step is to compute the necessary values corresponding to the sample. Okay, and of course, the last step is to decide whether or not the null hypothesis should be rejected or not. And of course, this should be reported in the context of the problem. Okay, so let's now talk about each of the steps mentioned. Okay, the first step really is to understand the problem. From this, you identify, okay, so the first step really is to understand the problem. From this, you identify what parameter is most relevant to investigate and what is the context surrounding it. For example, a problem might call for the investigation of the mean of a population, and one may want to know how this mean compares to a certain value. Is it equal to 0? Is it equal to a constant k? Or is it greater than or less than a constant? Do we know the variance of this population? The problem could also call for the comparison of two population means, as in the case of the Portland cement example, where we are comparing the means of two factor levels, namely the original formulation and the modified one. Now, again, we ask if the variances of the populations are known and whether they are equal. We could also be looking at comparison of proportions. Say we want to compare the rate of infection between two populations or the defect rate for two variations of a process. We could also be interested in the variability of a population or comparing the variability of two populations, in which case our parameter is the variance. Okay, now I show here a tree diagram summarizing the different parameters that could be of interest in a hypothesis test. So as you can see, in the leftmost, you have proportions. You can also be interested in the means, or you can be interested in the variance. So let's look at this branch here. Okay, under means, you could be looking at a single mean, and you should determine whether you know the variance of the population. If not, how big is your sample size? Is your sample size greater than 30? Or is it greater than or equal to 30? Or is it less than 30? Now, you can also be comparing two means, okay? And the data that you are using could be from unpaired observations. And then, of course, you have to know what the state of the variance, okay? Whether or not you know the variance of the two populations. Now, if it is unknown, do you have an idea of whether or not they are equal? Okay. There's also another branch here for when we are looking at paired observations. And then, of course, you have variances where you can compare either two populations or just a single population. Same is true with proportions. You could deal with one population or two populations. And then, of course, there are qualifiers here. Okay, so let's go back to the Portland cement example. In this experiment, the engineer wanted to determine the impact of adding a polymer latex emulsion during mixing to tension bond strength of the mortar. The original and the new formulation are the factor levels, okay, of the factor, which is tension bond strength. Now, suppose that although unknown, we could assume that the variances of the two formulations are identical. Then we are dealing with, well, the parameter that we are interested in is definitely the mean. And of course, we are comparing two populations, so two means. And we have unpaired observations. And we don't know the variances, but we can assume that they are equal. Okay. So now we have identified the parameter. Let's go to the next step, which is to state the null hypothesis. And along with this step is actually the third step, where we specify an appropriate alternative hypothesis, H1. So again, we wanted to compare the two means of the populations, right? Okay. So more formally, this can be stated as H naught would be mu1 is equal to mu2. And H1 is mu1 is not equal to mu2. Okay, so the first statement here is the null hypothesis. And the second statement is called the alternative hypothesis. Okay, so the null hypothesis is basically that the mean of population 1 is equal to the mean of population 2. That is, there is no difference between the means or the bond strengths of the two formulations being investigated in our example. And the alternative hypothesis is that there is a difference. Okay, so as you can observe here, if the alternative hypothesis is true, it would be true, okay, when either mu1 is greater than mu2 or mu2 is greater than mu1. So this is actually a case of a two-tailed hypothesis test. Okay, so we had a two-tailed test, and of course we can also have a one-tailed test where the alternative hypothesis is either just mu1 is greater than mu2 or vice versa. Now, these statements represent comparison of two populations. The hypothesis can also represent test for one population. In that case, you won't have mu2 here. It will be a constant, so it can either be a single mean one-tailed test or single mean two-tailed test. The next step is to identify the significance level. And we usually call this alpha. Okay, so the significance level, or alpha, is also the probability of type 1 error for the experiment. Now, the significance level is the probability of rejecting the null hypothesis, given that the null hypothesis is true, and usual values for alpha are 0.05, 0.1, or 0.01. Now, suppose that for our Portland cement example, we set our alpha at 0.05. Now, along with the specification of alpha is the specification of the beta value or the probability of type 2 error. Now, the type 2 error is basically the probability of failing to reject H naught when H naught is actually false. Okay? And of course, we want this to be suitably small. Now, we have what we call the power of a test, and this is related to the beta value. This is just equal to 1 minus beta, and this is equal to the probability of rejecting H naught when H naught is actually false. Okay, now the next step is to identify the test statistic. Okay, and as you will see later on, the test statistic will depend on the parameter of interest as well as the distribution, the assumed distribution of the population. Now, going back to our Portland cement example, since our parameters are the means of two populations with unknown but equal variances, our test statistic is T naught equals y1 bar minus y2 bar over the square root of the quantity s1 squared over n1 plus s2 squared over n2. For the other cases that I mentioned earlier, in the tree of different hypothesis tests that you can do, the test statistic would vary. And you can find this test statistics, and you can find this test statistics as well as the explanation as to how they were derived. And you can find this in the Applied Probability and Statistics by Montgomery. Okay, so we're done with the first 5 steps. Let's now move on to the next step, which is stating the critical region. So the critical region is just the set of values for the test statistic for which we will reject the null hypothesis. Okay, so let's look at this graph. Suppose that our population has this distribution here, and this is a t distribution, okay? This here is the critical region. And the area of the critical region is actually alpha, okay? The significance level. And we determine the values here, okay, of the critical region such that this value would lend the area of the critical region here equal to alpha, okay? And this is where, so for a two-tailed hypothesis test, then we would have alpha over 2 on the left side and alpha over 2 on the right side. These values would just be negative t of alpha over 2 with degrees of freedom n1 plus n2 minus 2. And on the right side, you have t alpha over 2 n1 plus n2 minus 2. Okay. Now we know the formula that we want to use for determining the test statistic as well as the critical region. Now let's compute the values for the sample that we have. So let's say that for the Portland cement example, this is our data. So we have 10 observations each for modified mortar and unmodified mortar. Okay, so we just employ the formula for the corresponding test statistic. And this here is actually the pooled standard deviation. You can also find the formula in Montgomery. Okay. So N1 and N2 are basically just the sample sizes for the two populations. So this would be 10 and 10. Okay. And we compute S1 squared and S2 squared, which are the variances of the two populations from the data. And this turned out to be 0.1 and 0.061. And we have here N1 plus N2 minus 2. This would just be equal to 18. Okay, 10 plus 10 minus 2. And this whole thing here is 0.081. So getting the square root of this will yield a sample standard deviation of 0.284. And now we just plug this into our equation for obtaining the test statistic that I showed you earlier. Okay, we plug in the value of the mean for the modified mortar, the mean for the unmodified mortar formulation. We have the pooled standard deviation, and then we plug in the sample sizes here. And we get the value of T naught, our test statistic, equal to negative 2.2. Of course, you can do this manually, or you can just do it using Excel or other software such as R or any other statistical software. Okay, so our critical region is what? Now we have to determine our critical region, no? So our critical region can be obtained using the formula that I showed you earlier. Okay, and that yields negative 2.101 to 2.101. Okay? As I mentioned earlier, you can do the calculations in other softwares. Okay, so I just inputted here the formula for our pooled standard deviation in R, and then the formula for our statistic, and then this one is our critical region. I just obtained the 2.5% percentile to the 97.5th percentile with 18 degrees of freedom for a t distribution to get the critical value. Okay, so remember, on the left side, you have alpha over 2, and that is 0.025, and then same is true on the right side. Okay, okay, so we have our values for our t-statistic, our critical region, and now we decide whether or not we reject H0, okay, and state our conclusion in the context of the problem at hand. Okay, so we computed our test statistic to be negative 2.20. Okay, and obviously this is within our critical region. Okay, so what do we say given our values? Given that our test statistic is within the critical region, we then reject H0. And our H0, remember, is mu1 is equal to mu2. So this means that the two formulations do not have equal tension bond strengths. And since it's on the left, okay, the new formulation actually reduces bond strength. Remember, mu1 is the mean of the modified formulation. Since our test statistic has a negative value, that means that the difference between mu1 and mu2 is actually negative, which means that our second mean is higher. All right, we stop here and we will continue in the next video where we will talk about confidence intervals and the use of the p-value method. Till then.